Okay. Hello, everybody. This is a presentation about the applications of intermolecular forces. Um, so, intermolecular forces, what's kind of important to remember and review really quick is that there are different kinds of intermolecular forces that exist, where we have the London dispersion forces. We've got induced dipole, dipole, hydrogen bonding, and then we've got the ionic forces that exist. So it's important to keep those in mind. And if you don't remember, go ahead and review which of those are stronger than the others, because that's a lot of where we get our applications from. But once you've reviewed that, you can go ahead and keep watching this video. Something I wanted to start off with was an analogy. And beware, there's spoilers here. This is about the Avengers. If you guys have seen Spider-Man Homecoming with Tom Holland, basically there's a scene in that movie where Spider-Man, like a boat gets chopped in half pretty much by the laser. And Spider-Man tries to go and he sticks everything together as strong as he can. And then he's holding it together as strong as he can, kind of in the middle. But he just isn't quite strong enough. And eventually the boat starts to break apart again. But Iron Man comes in and kind of saves the day and sends a bunch of his drones up that push everything back together. They're strong enough to hold things together. And that's one of the main concepts about the applications of intermolecular forces. We have intermolecular forces that, as they increase in strength, we begin to see different outer, what's the word? Applications of what actually happens. So there are several different areas that we'll begin to see differences in. So the properties, the outward properties that we see that are affected by either increased or decreased intermolecular forces is we see solubility, um, we see surface tension be affected, we see adhesion and cohesion, capillary action is affected, viscosity is affected, and volatility. And if you don't remember what these are, don't worry, we'll go over them during this review. But it's important to keep in mind what intermolecular forces are. So intermolecular forces are, let's say you have like water, for example. We're not talking about the bonds that exist between oxygen and hydrogen in H2O. We're talking about the forces that exist electrostatically between separate molecules of H2O. So how H2O interacts with another H2O particle, or a hydroxide end to a different molecule. So an OH at the end of a different molecule. All of these different interactions, if you remember from the last unit, they have different strengths. But remember, we're not talking about covalent bonding or ionic bonding. It's the forces that exist electrostatically between molecules. So first we're going to go over solubility. So solubility, the important thing to remember is that like dissolves like. So polar substances are more likely, we'll get to that, why it's more likely. It's not always the case that it like is 100% soluble in something if it's polar or if it has a polar piece. Polar things are able to be mixed with other polar substances. And the same goes for nonpolar and nonpolar. This is why we see interactions of like water and oil. We see them not mixing is because the polarity of the two substances. Water is polar, and oil, like vegetable oil, is non-polar. So they don't mix together. When you try and stir it up, even it might make like bubbles for a second, but then all of the oil will eventually come back together and aggregate in one area, and the water will be in another. So I kind of mentioned this earlier, and it might have been confusing. So just so you know, polar substance, if something or something will mix with something else that's polar, if they're both like 100% polar, obviously. But sometimes we have substances that have a hydrophilic piece to them and a hydrophobic. So hydrophilic is where it likes water. It's water loving. Hydrophobic is water hating. So it will repel water. And the reason that those exist is because of the polarity. Something that is hydrophobic is going to be nonpolar, and something that is hydrophilic is going to be polar. Since water is polar, it will mix with things that are hydrophilic, but not with things that are hydrophobic. So let's say we've got a carbon hydrogen chain that also has an OH connected to it. So the OH makes it polar. It's a hydrogen bond, or it creates a spot where something can hydrogen bond. But if there's so many other carbons and hydrogens, there's a lot of hydrophobic stuff in that molecule that might not make it 100% miscible. And so that's a term that you should be aware of. If something is miscible, it means that it at any quantity, these two substances can 100% mix. There won't be any of that not mixing that happens because of too much hydrophobic substance, even along with the hydrophilic. So if something has very like small amounts or no parts of hydrophobic ends, and it's all hydrophilic, then it'll be able to be miscible. So if it's polar, it'll be miscible if it's 100% polar. But then if you get the long enough chains, it might not mix. So that's solubility. Next, we have surface tension. And surface tension is a really important concept. And again, it's important to remember here as intermolecular forces increase, that we're going to see an increase in surface tension. That's kind of a theme that you'll be looking for a lot of these. Solubility was a little bit different because of the polar and nonpolar regions, but this goes into more of the strength of what forces are going on. So and this one makes sense. It's kind of like going back to that analogy. We wouldn't necessarily expect something just being held up by Spider-Man's webs to be able to be held up. But once something is pushed by Iron Man's drones that come in and push the ship back together, that was strong enough to keep them together. And he eventually like sealed it up with a laser and kind of like burned everything and kept it together. So that bond was enough to keep it together. And that could be compared to like Spider-Man's webs or London dispersion forces. So they're the weakest. They exist everywhere, and we can have enough of them that it's overwhelming and really strong. But typically, those are going to be weaker than our hydrogen bonds, for example. We could compare Tony Stark's drones to the hydrogen bonds that are a lot stronger, a lot more able to keep things together. And if it holds it together better, then the chances are things won't be able to break the surface of the water. We talked about it in one of our labs, and I think even one of our problem sets. We talked about how the cold paperclip is able to stay on top of the water while the hot one isn't. And the reason for that is because you need a certain amount of energy to break through that water. So if we heat up the paperclip, then it has enough energy that it'll break through the surface tension. But if it's cold, it doesn't have enough energy with its density. It doesn't have enough force pulling it down to beat the forces that are pushing up with the water. So surface tension is increased because of that increased bonding in between all of the molecules. It's holding them together better than the paperclip is able to sink through them. So I think that one makes sense too. If you have less strength in it, we see that with like we could compare that to like a grocery bag. If you put a milk jug in a single grocery bag and you aren't very careful with it, sometimes it could break through. It doesn't have enough there to support it and keep the milk jug from pulling through and pushing through the bottom because maybe you like jostled it or lifted it up and it brought the force down all at once, and it's not able to disperse over the entire bag, so it makes the rip, and then it just gets worse and worse for the bag till it eventually rips open. It's the same thing with surface tension. So next we've got adhesion and cohesion. And this one is a pretty interesting subject that I think when we went over it in lecture, I think I kind of struggled with this one and capillary action that we'll go over next. But I did a little bit more research on it and reviewed the slideshow. So basically, it's important to understand what the terms mean. Adhesive means that the particles are going to have interactions with unlike particles. And it doesn't mean that like they won't have interactions with their like particles as well. It just means that those with the unlike particles are going to be stronger. And an example of adhesion would be if you had a tube that you filled with water, you'll notice that you'll notice that the water begins to go up the sides and create a concave region in the water that would look like this, where it's kind of like, obviously this is only 2-dimensional, but in 3 dimensions, it would look kind of like a bowl, is more of what it would look like rather than just a U. And so that happens because the water is sticking to the walls of this glass. It's important that it's like a glass tube, because the molecules in glass are extremely polar, and it'll be able to pull the water up on the sides. The water will want to be connected to that because it's a more like good. It's a better state for the water to be in. The interactions are stronger on the sides with more polar molecules. So water will tend to do that. Cohesion, on the other hand, though, is when particles interact with like particles. So an example of that is mercury in that same glass tube would do the opposite. Instead of sticking to the sides of the glass, since it's going to be nonpolar, it'll create an upside down bowl. And it does that because as the water, it was getting pulled up the sides because it was attracted to the glass. Mercury, on the other hand, is going to be more attracted to itself than it is glass. Since glass is going to be polar, this one's going to be nonpolar. It'll hold to itself and create that upside down bowl. So you can kind of think of it as running away from the glass on the sides, is what the mercury would do. And again, it's really important to recognize adhesion for the water in the glass tube. It wouldn't necessarily happen in a plastic tube because it's not going to be stronger. It's not going to be more efficient for the water to be connected to the sides of the tube if it's made out of plastic. It'll be better for it if the tube is made out of glass. So that's when we see adhesion. And so just recognize the difference between these two, what they look like. You can look up pictures of it too. But adhesion creates a concave reaction, or like appearance in a tube, whereas cohesive particles will create more of a bowl, also called a convex. So just try and keep that in mind. Concave also has the A in it instead of convex. So maybe that's one way that you could try and remember it. Concave has the A, like an adhesive. And then you just remember that the other one is the other one. I don't really have any tricks for it. Capillary action has to do with that same idea of adhesion and cohesion. So it kind of makes sense that I must have just struggled understanding adhesion and cohesion in class. It makes sense why I didn't quite catch what capillary action meant very quickly. So capillary action has to do with kind of what I was talking about with those glass tubes. So I want you to imagine you have like a bowl or a liquid measuring cup, if you guys know what those are. It's not like the plastic or metal measuring cups that you get that are like 1 cup. Those are usually for solid. It's the one with the handle. It kind of looks like a pitcher. That's a liquid measuring cup. So imagine you have one of those. And then you get a narrow capillary tube, which if you donate plasma, for example, they'll prick your finger and they'll use a capillary tube that will suck the blood kind of from your, not suck it, but it'll, using capillary action is what it does, but I'll explain it in a different sense. It brings the blood up through the tube. So if we took the bowl of water, or the liquid measuring cup of water, and we dipped the capillary tube into the water, into the liquid measuring cup, what we would see is the water would actually rise above the point that it stops in the liquid measuring cup. So it's kind of weird. You'd probably see it go up like, I don't even know, depending on how far you dipped it, obviously, but you'd probably see it go like anywhere from a centimeter to an inch up the tube, up above where the water level in the liquid measuring cup ends. And the reason it does this is because of adhesion. Water inside that glass tube, really, it wants to stick to the glass tube, and since that's a better state for it to be in, it's willing to rise up. The amount of energy it takes to rise up and have the adhesive reactions with the glass, or adhesive force with the glass, because of its electromagnetic or because of its electrostatic forces, it'll go up the tube farther than the water level ends in the liquid measuring cup. So it's actually a pretty fascinating topic. You guys ought to go look into it if you're interested. You guys can go look up how trees use capillary action. It's a similar thing that they talk about. The water is drawn up through tiny little, I don't even know what to call them, like capillaries, pretty much, in the tree, and it'll get the water throughout all of it, even though that's going against the force of gravity. The idea is the forces in between the glass and the water, or in the wood and the water, it's enough to cause it to want to go against the force of gravity, because it's a better state for it to be in. Even if it could just rest, it's more advantageous for it to be at the higher levels. So again, we're kind of back at the idea of increasing intermolecular forces. Again, remember, just as a reminder, intermolecular is between two H2O particles, and not like the interaction between O and both H's. That's not what we're talking. That would be an intramolecular force. This is the intermolecular, just as a reminder towards the end. So increased molecular forces equal increased viscosity. And what viscosity is imagine like gasoline versus honey, where gasoline is really able to, or while gasoline is like very thin liquid, honey is super thick and like sticks together really well. And that really is the idea of viscosity. The higher your intermolecular forces are, the more the molecules are going to want to stick together. So like the thicker it'll appear and feel. So I think that this one's pretty like common sense. If we even use the word stick together when we talk about intermolecular forces, and that's what viscosity is. It's more likely to stick together if the intermolecular forces are higher. And this goes along really well with the next topic. They really aren't too different in reality. The final topic for the day is volatility. And you guys might remember we had the example of the lighter. Basically, what volatility is it goes over how easily a substance will vaporize. So increased volatility is actually correlated with increased vapor pressure, but weaker intermolecular forces equal higher volatility. So again, it's just the opposite of this viscosity. If it's weaker, if viscosity had weaker intermolecular forces, we would see a decrease in viscosity. This one, you kind of see like the inverse. They're not sticking together as well. So volatility increases if they aren't sticking together very well. And what vapor pressure is how like much pressure is being placed on the substance and to get outside of whatever container the gas is in. Um, and we get increased vapor pressure because of increased volatility. If more of a substance is vaporizing, there's more vapor, and gases we know have more energy. They're bouncing off the walls. They're bouncing off of everything. So this will make sense. If it's not sticking together as well, it's trying to bounce away from each other. It's trying to get away and diffuse. We're going to know that vapor pressure is going to increase since it's not trying to stick together. It's going to expand like a gas expands. So that's all I have about these. Hopefully this was a helpful review, and good luck with everything on the final. I don't think that we'll see this again until the final. We've already taken exam 2. So good luck.